Lecture 10-1, Gases and Gas Laws. The following are elements that exist as gases at 25 degrees Celsius and 1 atmosphere pressure. The monatomic gases comprise the noble gases, which are helium, He, neon, Ne, argon, Ar, krypton, Kr, xenon, Xe, and radon, Rn. Although oganesson, Og, element 118, is at the bottom of the column called noble gases, we do not have enough information about it to know what state of matter it would exist as under the same conditions. The diatomic gases are hydrogen, H2, nitrogen, N2, oxygen, O2, fluorine, F2, and chlorine, Cl2. Gases have four basic physical characteristics. First, gases assume the volume and shape of the containers they are put into. Second, gases will mix evenly and completely when confined to the same container. Third, gases are the most compressible state of matter. Fourth, gases have much lower densities than liquids and solids. The kinetic molecular theory of gases has four postulates. First, a gas is composed of molecules that are separated from each other by distances far greater than their own dimensions. Thus, molecules can be considered as points. That is, they possess mass but have negligible volume. It is like looking at a starry night in which the stars are spaced far apart and look like points. Yet we know they have mass and volume, though the volume is small compared to the vast expanse of space. Second, gas molecules exert neither attractive nor repulsive forces on one another. Third, gas molecules are in constant motion in random directions. Collisions among molecules or the container are considered to be perfectly elastic. That is, there is no loss of total momentum or conversion of energy in the collision. Fourth, the average kinetic energy of the molecules is proportional to the temperature of the gas in kelvins. Any two gases at the same temperature will have the same average kinetic energy. Pressure is force divided by area. Pressure is measured using a barometer. The SI unit of pressure is the Pascal and has the dimensions of a Newton divided by meters squared. It is an exceedingly small unit of measurement, as will be shown shortly. The atmosphere is more often used to measure pressure. It has three conversion factors. First, 1 atmosphere equals 760 millimeters of mercury, mmHg. Second, 1 atmosphere equals 760 torricelli, torr. From this you can deduce that 1 millimeter of mercury equals 1 torricelli. Third, 1 atmosphere equals 101,325 pascals. Thus you can see that the Pascal is small compared to the atmosphere in measuring pressure. Gas laws. The following are gas laws for comparing one gaseous state to another. All temperatures must be in Kelvin. These equations are used when there are changes of state or amount of gas present. The first is the combined gas law. It is pressure 1 times volume 1 divided by moles 1 and temperature 1 equals pressure 2 times volume 2 divided by moles 2 and temperature 2. Avogadro's law is when pressure and temperature are held constant such that volume and amount of gas are changing. The equation is volume 1 divided by moles 1 equals volume 2 divided by moles 2. Boyle's law is when the amount of moles and temperature are held constant and pressure and volume change. The equation is pressure 1 times volume 1 equals pressure 2 times volume 2. Charles' law is when the amount of moles and pressure are held constant and volume and temperature change. The equation is volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. Remember that these temperatures must be in Kelvin. Finally, Gay-Lussac's law is when the amount of moles and volume are held constant and pressure and temperature change. The equation is pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. Again, temperature must be in Kelvin. The conversion from degrees Celsius to Kelvin is Kelvin equals degrees Celsius plus 273.15. Gas law calculations 1. A sample of chlorine gas occupies a volume of 946 milliliters at a pressure of 726 millimeters of mercury. Question: what is the pressure of the gas in millimeters of mercury if the volume is reduced at constant temperature to 154 milliliters? In this problem, only pressure and volume change, thus we will use Boyle's law, which is pressure 1 times volume 1 equals pressure 2 times volume 2, where pressure 1 is 726 millimeters of mercury, volume 1 is 946 milliliters, and volume 2 is 154 milliliters. The unknown is pressure 2. Solving for pressure 2 equals 726 millimeters of mercury times 946 milliliters divided by 154 milliliters, which equals 4,460 millimeters of mercury. Note that the volume units cancel each other in the division, leaving units of pressure, millimeters of mercury. This is appropriate unit for pressure. Also note that the pressure is expected to increase as the volume decreases, because pressure and volume are inversely related. Gas law calculations 2. A sample of carbon monoxide gas occupies 3.20 liters at 125 degrees Celsius. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? This is application of Charles' law, which is volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. However, since temperature is unknown, we will use the inverse equation to avoid calculating the inverse temperature and forgetting that it was the inverse. The equation we will use is T1 divided by V1 equals T2 divided by V2. Thus, we can solve for T2 directly without using the inverse. Volume 1 is 3.20 liters. Temperature 1 is converted to Kelvin, giving 125 plus 273 equals 398 Kelvin. Volume 2 is 1.54 liters. Solving for T2, we get T1 times V2 divided by V1, which equals 398 Kelvin times 1.54 liters divided by 3.20 liters. The value of T2 equals 192 Kelvin. Conversion back to Celsius is temperature in Kelvin minus 273, which equals negative 81 degrees Celsius. Note that the temperature and volume are directly proportional, so the decrease in volume would come with a decrease in temperature. Gas law calculations 3. Ammonia burns in oxygen to form nitric oxide, NO, and water vapor. How many liters of NO are obtained from 1 liter of ammonia with temperature and pressure remaining constant? The chemical equation is 4NH3 gas plus 5O2 gas yields 4NO gas plus 6H2O gas. All that is directly given in the equation is one volume. How can we calculate another volume without additional information? That information comes from the chemical equation in the form of moles from the stoichiometric coefficients. There are 4 moles of ammonia, 5 moles of oxygen, 4 moles of nitric oxide, and 6 moles of water. Thus, the equation to use is Avogadro's law, which is V1 divided by N1 equals V2 divided by N2. All we need to do is to solve for V2. Thus, V2 equals V1 times N2 divided by N1. Solving for V2, we get 1 liter NH3 times 4 moles of NO divided by 4 moles NH3, giving 1 liter NO. Gas law calculations 4. Ammonia burns in oxygen to form nitric oxide, NO, and water vapor. How many liters of oxygen are used to produce 4 grams of NO, occupying 1 liter of volume? The chemical equation is 4 NH3 gas plus 5 O2 gas yields 4 NO gas plus 6 H2O gas. Since we have an amount of one gas, volume of a second gas, and a balanced chemical equation, we can use Avogadro's law. The mass of NO will have to be converted to moles of NO, and the molar ratio of oxygen to NO will be used to determine the amount of oxygen used. The molar mass of NO is 14.01 grams per mole nitrogen plus 16 grams per mole oxygen, equaling 30.01 grams per mole NO. The number of moles of NO is then 4 grams of NO divided by 30.01 grams per mole, giving 0.133 moles NO. To calculate the moles of oxygen, we will use the molar ratio from the balanced chemical equation, which is 5 moles O2 divided by 4 moles NO. Thus, the moles of oxygen equals 0.133 moles of NO times 5 moles O2 divided by 4 moles NO, giving 0.167 moles O2. The volume of oxygen is then V1 times N2 divided by N1, which is 1 liter times 0.167 moles divided by 0.133 moles. The answer is 1.25 liters of oxygen. Gas law calculations 5. A certain light bulb containing argon at 1.2 atmospheres and at 18 degrees Celsius is heated to 85 degrees Celsius at constant volume. What is the final pressure of argon in the light bulb in ATM? Since temperature and pressure are changing, we will use Gay-Lussac's law, which is P1 divided by T1 equals P2 divided by T2. Solving for P2, we have P1 times T2 divided by T1. Remember, temperatures must be converted to Kelvin. Thus, T1 equals 18 plus 273, which is 291 Kelvin. And T2 equals 85 plus 273, which is 358 Kelvin. Putting these values in the equation, Solving for P2, we have 1.20 atmospheres times 358 Kelvin divided by 291 Kelvin, which equals 1.48 atmospheres. The ideal gas equation. The assumptions behind the ideal gas law come from kinetic molecular theory of gases. The formulation comes from the gas laws. Avogadro's law states that volume is directly proportional to the number of moles. Boyle's law states that volume is inversely proportional to pressure. Finally, Charles' law states that volume is directly proportional to temperature. Putting these together, we have that volume is proportional to moles times temperature divided by pressure. To make the proportionality an equation, a proportionality constant is needed. For the gas laws, the proportionality constant is the gas constant, having the symbol R and a value of 0.082056 liter atmospheres per mole Kelvin. When using this value for the gas constant, pressure must be in atmospheres, volumes must be in liters, temperature must be in Kelvin. After inserting the gas constant and multiplying each side by pressure, we get the ideal gas law. Pressure times volume equals moles times the gas constant times temperature. The ideal gas equation is used for gas calculations under static conditions when 3 of the 4 variables, pressure, volume, moles, and temperature, are known. Ideal gas calculations 1. A sample of chlorine gas, Cl2, is pumped into an evacuated 500 milliliter flask. The resulting pressure is 258 millimeters mercury at 22.3 degrees Celsius. How many moles of chlorine gas are in the flask? What is the mass of the chlorine? What is the density of the chlorine? Because the conditions are static, we will use the ideal gas law, PV equals nRT. Solving for N, we have N equals pressure times volume divided by R and temperature. N equals PV over RT. Pressure must be expressed in atmospheres. Thus, pressure equals 258 millimeters of mercury divided by 760 millimeters of mercury per atmosphere, giving 0.3395 atmospheres. Volume must be in liters. Thus, volume equals 500 milliliters divided by 1,000 milliliters per liter, giving 0.500 liters. Temperature must be in Kelvin. Thus, temperature equals 22.3 degrees Celsius plus 273.15, giving 295.45 Kelvin. Solving for moles, we have N equals 0.3395 atmospheres times 0.500 liters divided by 0.08256 liter atmosphere per mole Kelvin and 295.45 Kelvin. The answer is 7 times 10 to the negative third power moles of chlorine. The answers to part B and C are on the next slide. Ideal gas calculations 2. The mass of chlorine equals the number of moles of chlorine times the molar mass of chlorine, which is 7.00 times 10 to the negative third power times 70.90 grams per mole chlorine, giving 0.496 grams chlorine. The density of the chlorine gas is mass of the chlorine divided by the volume of the chlorine, which is 0.496 grams chlorine divided by 0.500 liters, giving 0.992 grams per liter chlorine gas. Standard temperature and pressure, STP. The conditions of 0 degrees Celsius and 1 atmosphere are called standard temperature and pressure. Experiments show that at STP, 1 mole of an ideal gas occupies 22.414 liters. This value of 22.414 liters per mole of gas is called the molar volume of a gas at STP. For example, the volume of the chlorine gas in the previous example at STP would be 7 times 10 to the negative third power moles chlorine times 22.414 liters per mole, giving 0.157 liters volume. This decreased volume is expected because the pressure was increased, which would cause a volume decrease, and the temperature was decreased, which would also cause a volume decrease.